Yo, all right, video 4, integration by parts. Going to learn how to integrate integrands of the form exponential times trig, and going to kind of see how this plays out. So let's just get right after it. So if we have the integral, I'll try that again. If we have the integral of e to the 2x times maybe cosine of 3x dx, all right? So this now is of the form exponential function times trig function. All right, so we have a product. So again, you'd look to exhaust all your other possibilities. There's a normal U substitution work here. It does not. Do I recognize a function whose derivative is this? I do not. So every integration technique that we have learned to date is really not going to handle this. So you're thinking, you know what? Let me try integration by parts. Seems to work when all else fails and I have a product, right? So what do you pick, right? That's been kind of the debate on all these problems we've been doing. Well, let's pretend like we don't know. And let's let u equal maybe the exponential part, e to the 2x. So then dv now, if you remember, has got to be the rest. You have to pick a u and a dv so that accounts for everything. So then it would be cosine of 3x dx, right? So you've successfully expressed this integral as the integral of u, and then all of this stuff is dv. Okay, so once we have our u and our dv, we're going to compute du. The derivative of e to stuff is going to be e to stuff times the derivative of stuff, so times 2. So I'll just be cool and write it like that, 2e to the 2x. Since it's du, it's really a differential. We have to do times dx, right? When there's a du, there's got to be a dx, just like when there's a dv, there's got to be a dx. All right, so now we got to figure out what v is. So remember, to go from dv to v, we're integrating. So do I know a function whose derivative is cosine of stuff? I do. It's going to be sine of stuff times 1 over the derivative of stuff, right? So a little linear u substitution there if you don't understand where I got that from. All right. Again, we don't have to do the constant of integration because that'll come through in the formula. So now remember, the whole point of this is if you are able to express the integral as the integral of u dv, that's going to equal uv minus the integral of v du. That is the integration by parts formula, right? It was actually derived by the differentiation formula for a product and then just kind of working backwards. So that's what we got. So let's apply it. So we have u times v. So multiplication is commutative. I'll spruce as I write this. So that would be, let's see, 1/3 e to the 2x times the sine of 3x, all right, minus the integral of v du. So the 1/3 and the 2, that can get pulled out of the integral. So I'm going to write that as 2/3 and then e to the 2x times the sine of 3x dx. So that's going to be v du. So you take a look at that, right? And the whole idea is, all right, well, let's look at this integral right here. And we want to ask ourselves, did it get better? And if you look at it, it kind of looks the same, right? So it didn't really get any better. And all of the problems that we have been doing to date, when we successfully picked u, the integral got better. All right, but here's the deal. It didn't get better, but it really didn't get any worse. You still have an exponential whose exponent is linear. You still have a trig function whose internal function is linear. So it's kind of the same. All right, so the same type of difficulty or structure, whatever you want to call it. I don't know why I'm putting same in quotes, but I will. So that's actually a good thing. All right, so if it's the same or better, then integration by parts could work. So I'm telling you this is a good thing. So you're like, all right, well, then what do I do? Well, if you think about it, right, what did you have to do when you had this? If this is the same, you probably should do what? Hopefully you're saying do parts again. So let's do it. So let's let u, which I'll call u dot, just to distinguish it from that u, let's let u equal, and I want to pick in the same manner, so e to the 2x, and then dv, which I'll call dv dot, all right, is going to be the rest of the stuff, sine of 3x dx. All right, so now du, right, the derivative of e to stuff, that's going to be e to stuff times the derivative of stuff using the chain rule there, okay? And then v dot, I'm going to integrate now. So do I know a function whose derivative is sine of stuff? I do. It's going to be negative cosine of stuff times 1 over the derivative of stuff. Again, that's because that's a linear u substitution that we're essentially doing in our head. All right. Or you could just say we're just finding the antiderivative in our head, however you want to think about it. Okay. And remember, the derivative of cosine is negative. So the derivative of negative cosine would be negative sine, which is positive sine. So that's where that's coming into play. So now, again, you have this integral expressed as the integral of u dv, or better yet, u dot dv dot. So same deal here, right? U dot dv dot is going to equal u dot v dot minus integral of v dot du dot, right? So my v's and my u's look very similar here. That's horrible. U dv, so I'll make my v's in red. uv minus integral of v, and then that's du, okay? All right, so let's go get them. So here we go. U times v. So that's going to be negative 1/3 e to the 2x cosine of 3x. So that's my u times v minus the integral of v du. So I can pull out the negative 1/3 and the 2. So that would be plus 2/3. And then I get e to the 2x and then cosine 3x dx. Now, before I forget, let's just make sure I write all the other stuff here, right? So I have 1/3 e to the 2x sine of 3x, and then minus, and this is the thing everyone always forgets, right? Minus 2/3 times the expansion we just did here, right? This 2/3 affects all of this integral, so then it affects all of that expansion. So now let's take a moment and pause and be like, all right, let's take a look at the integral. So what happened here? Did it get better or is it the same? Well, it looks the same. And in fact, even better than that, it looks like it's the exact same thing that we started with. So we went in a complete loop, right? We're back to where we started with, right? It's the same exact integral. So, your instincts might tell you, oh man, that's not good. This didn't work. But that's actually a good thing. So it's a good thing to go in a loop. So we can kind of like file these types of integration by parts problems as like the loop problems, where you do parts twice and you get what you started with. That's a good thing. Now you might be asking, why is it a good thing? Well, let's write what we have. So we have the integral of e to the x cosine 3x, right? So I'm going to kind of write the integral of e to the x, e to the 2x, cosine of 3x, right? That's what we have. That's what we started with. And doing this parts thing, we got all of this stuff. So I'm going to kind of sort of spruce this, and that I'll distribute this blue negative 2/3. So I have 1/3 e to the 2x sine of 3x, right? And then minus, so that's going to be plus 2/9 e to the 2x cosine of 3x, and then minus 2/3 times plus 2/3, it's going to be minus 4/9 integral e to the 2x cosine of 3x dx, right? So this is what we have. And you'll notice that this integral here, as we said, is the exact same thing as that integral there. There's just a different constant out in front. So what in the world? How can this possibly be a good thing? We have an integral in terms of an integral. We don't want that. We want to be able to do this. Well, you got to kind of think 8th grade algebra here, right? So you're trying to solve for this integral. So this thing I underline blue is like your variable. It's like your super x. You want to solve for x, right? So what do you have to do? You got to get all the x's on one side, right? So what I can do is I can take this and I can add this over, right? This minus 4/9. Why don't I just do this? Why don't I say, hey, you know what? I'm going to work both sides of this equation. I'm use some skills I learned in 8th grade algebra. So I'm going to add 4/9 integral e to the 2x cosine 3x dx. If I add it to this side of the equation, that's just summing to 0. Over here, I'm going to write plus 4/9 integral e to the 2x cosine 3x dx. And you're like, well, what the heck do I do with that? Well, this is one of these integrals. This is 4/9. Maybe it's better for us to think of this as 9/9, right? So that means I'm going to get 13/9 integral e to the 2x cosine 3x dx, right? There's no reason why I can't do that, right? Just like any other unknown that I want to solve for. And then over here, I got this stuff. 1/3 e to the 2x sine of 3x, and then plus 2/9 e to the 2x cosine of 3x. Okay? All right, so that's looking good. So you're like, well, what'd you just do? Well, think about this now. There's no more integral on this right side, and the integral that we want to solve for happens to be right here, right? You're like, well, what do I do with that 13/9? Well, again, back to middle school algebra here. Just multiply both sides by 9/13, right? And then that's going to whack it out on the left side, and you're going to get it on the right side. So you're going to get the integral of e to the 2x cosine of 3x dx. And then it's going to be 9 over 13. I didn't show it, right? 9 over 13. I would cancel here. 9 over 13 times all of this. 9 over 13 times all of this. So 1/3 e to the 2x sine of 3x plus 2/9 e to the 2x cosine of 3x. Boy, my handwriting is getting terrible right now. And that's it. And you're like, holy moly. Okay, that's basically your answer. Now, there's one thing that we're missing here, and maybe you can kind of help me out, right? So it was a little weird how we got it. You could almost say like we backdoored it, right? I mean, we never actually found an antiderivative, so to speak. We did some mystical algebra, though it wasn't so mystical because it's stuff you learned in middle school, right? But we have the answer here. But this is an indefinite integral, so something looks a little weird over here. Right. And what looks weird, hopefully you're thinking, oh, you need plus C, right? So we have to go ahead and do plus C. So it's a little weird because of the way we backdoored it that you might forget to think to add the plus C. But once eventually you get that integral solved for, then just add that constant of integration. All right, so that is an example of doing an integration by parts problem where going in a loop helps. So you do it once and you get an integral that looks almost identical, right? Same type of structure, same form. So you'd say it's the same. So you don't give up, you try it again, and then you go in a complete loop. And when you go in a complete loop, that means that's a good thing. You're going to be able to go ahead and solve for the integral. All right. Now, to be honest, there's lots of mistakes that happen when you do these problems. You forget to distribute constants, you forget the negatives and things like that. So you got to be careful. All right. I'd be shocked if I actually didn't mess up here and screw up a constant or not. Hopefully I didn't. If I did, I will delete the video. If I didn't, I'll keep it up. But it's very easy to do that. So you got to, write big, take your time, use a lot of paper, and get after it. All right, so that is integration by parts when going in a loop helps. So this is what you can do right now. I'm not gonna do this one for you. All right, but the problem I want you to do, we'll switch it up. Let's do the integral of e to the, we won't go too nuts. Maybe we will. 1/2 x. Oh no, fraction. And then what we had cosine before, I think. So maybe this time we'll start with sine and just change the constant 5x dx. All right, we'll call this example. All right, doesn't want me to write that. Anyway, all right, so go get it. So there's your problem, all right? And this is the problem that I'm going to have you guys submit on Tuesday. We'll do it as a class on Tuesday, but if you're not able to attend that session, then just go ahead and submit this problem. And what you'll see is that all of these integrals of the form eventually, all right, all of these integrals of the form e to the ax times sine of some other constant bx, right? They actually they look similar. So their solutions look very similar. Now, you'd have to do more than 2 just to see it. But if you ever pick up a calculus textbook, especially the old ones, you'll see this on either the front cover or the back cover where it's an integration formula. And they actually tell you what this equals to, okay? Because there's a pattern. They're all very similar. Now, the other thing that I didn't talk about is I didn't say, hey, so it turns out it looks like we picked the trig to be the u and the dv. I'm sorry, the exponential to be the u and the dv to be the trig part, right? That's kind of how I did it in the last one. So like if you're following that logic, you're going to let u equal e to the 1/2 x, right? I'm kind of starting the problem for you a little bit. And then dv obviously would be the rest of the stuff, right? So you might be thinking, okay, when we have exponential, right, times trig, that we're going to want to let the exponential be the u part. So now I'm going to throw this out there to you. In addition to finishing this problem, switch it up, all right? Do it this way, but then go ahead and do it this way, where you pick the u to be the trig part and see if you're able to get the answer. All right. And I'll be a little, spoiler alert here. It actually turns out it doesn't matter what you pick in this one. You can pick U to be the exponential, or you can pick it to be the trig part. You're still going to successfully go in a loop, and you're still going to be able to figure it out. All right. So that's the first one that we saw where it actually didn't matter which, factor in the product that we picked. All right. So I've been rambling along. Go ahead, get this problem done. Again, if just we'll do it live on Tuesday if you want. Otherwise, do it on your own. Hand it in. Hope you guys are good. Stay safe.